All right, I am on a little bit early. Got a little bit of a halo effect going on with lighting here. We're in a slightly different spot of the DIY RM Heavy Industries garage. The 400 square foot workshop. So we'll, since I'm on just before noon, we'll sort of a bit of a check just to make sure everything's working. We'll wait for folks to start joining. Everybody, let me know if you can hear me well. I have changed my audio around from last time. I'm actually using a mini DSP right now for microphone. You mic here. Turn that video off. Hey, Brian. Hey, Daniel. Yeah, I did a quick recording and it seemed a lot better, so we'll use this. I've actually got a really nice large diaphragm Audio Technica microphone, and but it requires 48 volt and another interface, and I haven't gotten to the point where I've got that thing mounted on a shock mount boom hanging over my head, but maybe we'll get there at some point. So I should pull this up. Give everybody a little in-process picture here. We'll wait a few more minutes, let folks join. Yeah, the interface regime on this thing is already getting a little crazy. I actually have. Oh, I just remembered. I have one that one channel is broken, but the other channel works just fine. I might pull that one out. But then I've got two different brands. What I really just need to do, and I've thought about doing this, is to my mixer can serve as a digital interface too, and I may just have to go there one of these days. So we'll see. It is high noon, my time. So, and it's a weekend, so that means any minute now I can start enjoying some tasty adult beverages, but that's going to have to wait for a little longer. I've got to go pick up some stuff. Always got to be safe. So let's see, what time is it? We'll give a couple more minutes for folks to join. I see multiple viewers that have not said hello. Say hello in the chat so I know who I'm talking to here. Unless I can get to it. I can't seem to get to it. All I see is concurrent viewers. Hello. Okay. I don't want to butcher the pronunciation of anyone's name. Saraf, hello. I'm sorry if I got that wrong. George, hello. So we will get started. I would like to announce a PM me anything not related to the stream. I have enough things going on, and I'm just ADD enough where that's a rabbit hole I don't know if I want to go down just yet. Before we really get going, I would like to announce an unofficial DIYRM sponsorship. My DMM is now sponsored by BNC unofficially. There's a hilarious story there and an inside joke that I'm not going to tell. And so, yeah, there we go. I have fresh batteries. Let's just say that. So welcome everyone for joining. I've got what is hopefully a educational, fun hour of everyone watching me operate software, which is always the handiest. We're actually going to be, this is sort of the public unveiling of the yet to be named dual 18-inch front-loaded horn project that you see sort of sitting behind me. This is the first time the horn response inputs for that have been seen at length. They've actually, there was an oopsie on a previous video where I showed them and wasn't quite ready to show them yet because I hadn't done a lot of testing on the thing. But I have done enough testing now where I'm comfortable showing these off, and I don't have them on the screen. So we're going to talk about front-loaded horns for horn response, and this is a pretty complicated model, complicated thing to model. So I'm going to give everyone sort of the speech that I give for electrical simulation for finite elements. The simulations are only going to be as good as your inputs, and they're only going to be as good as the models take into account effects that are happening physically, right? So if you're doing a PSpice simulation and you are doing something that requires like some sort of fancy RF transistor, but you're using the basic model that is included as, you know, sort of a generic no-name device in PSpice, obviously your simulated results are going to be different. Horn response has a couple of things, you know, and this is a very difficult thing to simulate horns in general, right? There's a lot of math behind this, math that I won't pretend that I've ever known, and what little of it I did know has been forgotten long ago, since I mostly operate budget spreadsheets and things like project Gantt charts for my day job at this point. and I don't do a lot of engineering math. Having to help the eldest kid with high school math, it's like, oh, I remember how to do all of this. I don't remember what any of it is called. I remember how to do all of it. So now I'm relearning the names for things. So maybe I'll continue to help her all the way through high school and be able to delve back into sort of the collegiate level mathematics. Who knows? I don't feel like doing that, so we'll see. So the biggest thing you have to remember with horn response is that it assumes that the walls of the enclosure are rigid, perfectly rigid, infinitely rigid, and that the horn you've built is straight and round. Okay, so you've got when you build a horn, and when you simulate a horn like this, and then you actually build it, and you can see that my horn is built out of 18 millimeter Baltic birch, and it is not round, and it is not a straight shot. That there's going to be some differences, right? So, and even then, there's still going to be some sort of higher order modeling effects for the airflow and things like that it may or may not take into account. But David, in general, has done a phenomenal job, and the fact that he gives this thing away for free is amazing. So, if I'm ever where he is again and we can meet, he's got dinner on me for sure. And whatever bottle of wine he wants to pick off the menu, frankly, for as much as I've used this thing. So it used to be that if you're going to do a horn-loaded speaker in horn response, it was a lot of sort of trial and error to even remotely get the inputs started. The input to horn response can be a little challenging. It is a this interface doesn't, until you get the hang of sort of what means what physically, it doesn't make a lot of sense, right? So right now I've got a bass reflex. Recently, David has added an input wizard feature that is far more advanced. I don't remember which of the billions of versions of the program that came out in, but it's been quite handy and takes a lot of the pain and difficulty out of it. How do you determine QL? You can only input QL for a bass reflex box, which is what this record is, and larger boxes, 0.7 to 0.10, or QL of 7 to 10 is about right. Smaller boxes or some sort of heroic construction, you can get higher than that. Remember that, but we'll get back to that. As soon as I go to, let's say, a horn-loaded box, you can see that the QL thing here goes away, right? So you can't enter Q anymore. I don't know if David will ever add that feature, but we'll see. So the first thing to know is that, and let me calculate this horn window schematic, is that, as I said, actually, let me go back to this. He has added a input wizard that is really handy. Okay, so what I'm going to do is put that in and walk you through how to get this thing started. Right, so loudspeaker location, and he gives you sort of little hints down here. Free space, half space, quarter space, eighth space. Okay, this means that sort of the environment that the speaker is firing into. Free space is hanging in the open. There's no significant boundaries. I pretty much reserve free space for smaller speakers that I know are going to get flown, right? Like, if you're doing a true PA speaker, point source or something like that for a theater or something like that, this can start to actually be true free space. Most of the time I'm simulating in half space or even quarter space because that's the environment that you're in. This makes a difference sort of in the radiation impedance that the driver or that the mouth of the horn sees, and it sort of it'll it'll show you closer to real sensitivity and closer to real extension. Okay. So I'm going to choose half space here, although for this particular example, it doesn't matter much. And I'll actually show you an example, if I remember, of the differences between them. Loudspeaker type. Direct radiator means like a bass reflex box, sealed box, and some of the other sort of fancier enclosures that you can get to, but that's a whole nother set of videos. We're going to go horn loaded. Now here's where we have a lot of options, okay? Front loaded horn. What I've built is actually an offset driver, okay? It is not considered a front-loaded horn. Front-loaded horn means you've got a chamber firing into the horn, and the very end of the horn, the smallest area of the horn is what you're firing into, whether or not you have what's known as a throat adapter, something that goes between that to sort of neck it down to allow space for the driver for excursion, things like that. Is sort of, up to decision later, and we'll get to that. A backloaded horn, but the rear radiation from the driver is contained in a sealed chamber. Okay, there's an option to port it later, but we'll get to that. Okay, a backloaded horn is sort of the dub PA scoops that you see. You see these a lot with full range drivers. Where the back of the driver radiation goes through the horn path and the front of the driver is open to the outside world and allowed to radiate to the outside world, okay? Offset driver is like the front loaded horn, except instead of firing into the horn at the smallest end, the throat of the horn is what that's called, you're firing into the side of the horn somewhere along its length, okay? Synergy horn mid-ranges are offset driver horns. And so, again, that's going to be another video because we're not going to be able to get to all this. Tapped horns, again, these are all sort of variations on a theme. We're not going to be able to get to all of these in the same video because it's just going to take too long, and everybody's brain and mind, including my own, will explode. So we're going to go ahead and move on with the front-loaded horn. We're going to give it 3 segments, okay? This is in horn response. You can have up to four segments, as you can see. You can actually use the throat chamber to sort of simulate, help you with a 5th segment if you look at it that way. I'll show some of that later. It makes an impact. You'll see. So we're going to go 3 segments here. We're going to select the flare profile for each of the segments. And so you can choose the flare rate. Now, I typically simulate bass horns as conical horns. If you're being really, really accurate about it, for like the construction that I have behind me, that's actually technically a parabolic flare, but I'll show you in a second, or show you in a bit, that the differences between the two are pretty trivial, at least in most cases, but it is worthwhile to check. I checked on this horn, and the differences were almost nothing. Okay, so we're going to select those. The rear chamber, it can have acoustical lining or not. For bass horns, I tend not to put acoustical lining in there. That tends to cause them trouble with overheating the driver if you drive them hard, mostly because the PA use, they're going to get driven really hard for many, many hours, sometimes days at a time. And that acoustical lining can, although it'll smooth the upper end response out, you don't care because you've put an electrical low-pass filter on it. And it serves as sort of insulation and keeps all that heat in the box. And so that's bad. Throat chamber, on this one we'll give it a throat chamber. Throat adapter, sure. So now, here is our schematic, okay? Here is our classic front-loaded horn profile, right? We've got a sealed rear chamber. We've got, and I forget one of these, I forget which order they put them in, but one is the throat adapter, one is the throat chamber. And then here's our 3 conical sections, okay? This value here is S1. This is L12. This is S2. This is L23, S3, L24, S4, okay? And so when I say finish, and it has chosen their default loudspeaker, it has not put the real speaker parameters in there. When I select finish, it generates this file for you, which is really handy because you used to have to sort of know how to put all of these things in. And so I can calculate it, and lo and behold, because that is a beastly driver, and he sort of already knows which driver he's picking for this thing, he gets a pretty good response out of this. In fact, that's an excellent response out of this. But what you'll see is it's not really so much of a bass horn. It's got, 105, where's 102? F3 of 80 hertz. So, I would call this a kick if you were in the PA world. This is much more of a kick, or even low mid, depending on what you wanted to call it. But going back to that schematic diagram, you can see it has transferred everything in there. You can start changing this. Now, the easiest way to modify a horn in horn response is not to enter things onto this screen. I don't find that particularly easy at all. I hit Control E, and that pulls up an entry format that he calls the Loudspeaker Wizard, and you get these sliders. I find this to be far more useful because what you can do is you can go to the power, which is the SPL of the system, and you can start changing things, and you can see how the what's happening to the resulting frequency response. Okay, for instance, I just made S2 very large. In fact, S2 is now larger than S3. And if we go back and we look at the schematic for this thing, this is going to be a very funny looking horn, right? And you can see that that has been very bad for the frequency response. Like, you wouldn't want to do that, okay? But if you're not using his driver, this screen is a great way to input your parameters and sort of understand what you're doing physically very quickly, instead of entering them into the previous one and then hitting calculate and then trying to remember the way they were and things like that, and how much of a difference it has made and things like that, right? So we're going to go back to not a flower vase on its side here. And we're going to take this back to the horn-ish that was originally generated, okay? So I've chosen conical here, and I have no idea what the difference is going to be, but I'm going to change them all to parabolic, and lo and behold, whoops, release capture results, capture current results, input parameters. Now we're going to change them back. So tools, compare captured. I have now compared the difference between the parabolic and the conical expansion for those lengths, okay? Where I found that it actually starts to make a difference is if you're doing really long tapped horns, then it can make a difference. But very often I don't find this to be enough. Again, check, make sure that you haven't simulated something wrong, but I would check this pretty regularly, okay? So by itself, there is some rules of thumb for large bass horns, right? You see these all the time, rented out or printed out, about mouth circumference being quarter wavelength, and total length of horn being at least a quarter of a wavelength and things like that. But when you start to reduce this to practice, what this means is that nearly every bass horn out there is smaller than you'd want it to be. Okay, the mouth is smaller than you want it to be. The length probably isn't quite as long, and as a result, you end up with less than ideal responses. Like, again, I don't remember how much. Oh yeah, okay, I haven't broken this one yet. Like, this is a pretty ideal response. You're just not, for true bass horns, you're just not going to see these sort of really smooth responses. You're going to have more ripple to them. You're going to have more slope to them. And you're going to see all sorts of things that is a not perfect response, right? And you just kind of have to get over it. I wish that was the case, but physics is not just a good idea; it's the law. And you just kind of got to get over it. So I am going to go to. I don't know if I wanted to actually save that, but sure. It's not like I don't have enough records here at 887 different designs, and occasionally I do go through and delete them. But I have a few. So this is the horn that I have built that's behind me. And it is an offset driver horn. So I'm going to hit calculate here, and we're going to see this response. And first thing I'm going to do is go to the schematic, okay? So this schematic view confuses a lot of folks, I think, in horn response, because they don't realize what they're looking at. These circles here represent the driver. They represent the enclosure for the driver. Again, he's assuming everything's a round circle, right? They are, and it's sort of turned to look, instead of front way, it's turned to sort of look at you, right? And so I'm actually on this horn injecting the pressure from the driver into the point at S2, okay? I converted this horn to a front-loaded horn so you can kind of see the difference between the schematics. But when I do that, it puts the entry point into S1, which is too tiny. Okay, and we'll get to that in a second. That's compression ratio, and that's too tiny. So now you can see that this is the rear chamber. This horn is actually ported. It's a rear-ported, front-loaded, or rear-ported offset driver horn. It is not a simple design. We'll get to why I did that in a second. Yeah, so this is the schematic for the horn. You can see that the total box size is just under 800 liters, okay? On Wednesday, on my Facebook page there on DIYRM, I released a sort of tongue-in-cheek, laughing horn folding flowchart, which Brian mocked because he does these way cooler spreadsheets. In fact, he has a spreadsheet if we can convince him to release it for this type of fold. No pressure, Brian. I'm not trying to peer pressure. Peer pressure. Not trying to peer pressure. Yes, I am. Yeah. So these types of, when you're folding these horns, the way I have discovered that is sort of the easiest way to do this is I don't design the horn 100% in horn response and then blindly try and go fold it. Because that's an exercise in futility, especially for tapped horns, right? It's this iterative process where you determine sort of your maximum mouth area, you determine your maximum size, and that gives you a volume. And then you go into horn response and you start creating horns that are less than that volume, usually by somewhere around 10 to 20%. You're going to lose that much volume in trying to make the turns and wood for dividers and braces and things like that, right? So if I made a box that was outside exactly, or internal dimensions was exactly 788 liters, there was no way that I could fold that horn and keep it inside that volume. You probably have to make this box 950 liters in order to fold this horn and keep it inside that volume. And so there's this iterative process where you determine your envelope, you create a horn-like thing that's sort of close, and then you start going back and forth to determine whether or not you like the response, whether you're happy with the performance of the thing, and you can actually fit the thing into a box and build it. With Brian's great spreadsheets, that iterative process is a little less painful because it's much easier to shift panel dimensions around and just export the record, import it into horn response, and voila, resimulate it. Versus if you're trying to do a really fancy fold that's not covered by one of those spreadsheets, like the fold that I have here was not covered by one of those spreadsheets, and I don't know the Visual Basic behind those spreadsheets well enough to start creating one or modifying one, and so I ended up having to do this sort of a very painful graphical way. And I have an example of that. And I don't have SketchUp on this machine. But this is the example of how I did that, right? So the first thing I did was sort of create this 3D shape of the fold. Then I cut it in half and I started wrapping it around so that I could fit this thing into a box. And with enough tries, I could actually go back and forth, and you can see where I was. Let me zoom in on this some. You can see here where I was sort of playing with the S3 or S4 dimension here, the second to last dimension some, in respect to getting the magnet for the driver that I had for this speaker to get the magnet to fit. SB Audience was very nice and gave me access to some of their Rosso drivers, which I'll show you a data sheet for in a second. But the catch with that woofer is that the magnet's gigantic, which is awesome. Like, that's an awesome thing. But then when you try and put this into a rear chamber, you've got to fit that magnet in there. Okay, and so there's this iterative process that you do. All right, let me close out of there. So let me go back to the actual horn. So I'm going to run through some features in horn response that I don't know if a lot of people know are there. Okay, so the first thing I'm going to do is, actually, I'm going to turn editing on. So the first thing I'm going to do is show you this is the predicted response, and here, let me again zoom in on that, is some measurements I took. Now, take these measurements with a grain of salt, especially, do I prefer a compression driver with a good horn or a 3/4 inch dome treater with a good wave drive? Yes, I prefer them all. It depends on what I'm doing with them. If I'm doing high output PA speaker, obviously I will prefer the compression driver. If I'm doing a Synergy horn or co-entrant Unity style horn for home audio, I will probably still prefer the compression driver. But it all depends on the application, right? There is no, I have heard some phenomenal sound from relatively low-cost compression drivers that give you dynamics that a 3/4 inch or a 1 inch dome tweeter cannot hope to achieve, period. So this is the simulation versus the measurement of one of these horns. Down low, I actually think that it's probably a little bit closer than the response would indicate. There was a lot of change in response based on microphone position when I was doing this, which means where I was, I was doing this in my back alley, which you can't see because the garage door is closed behind me. But there is a 3-story apartment building next to me. There is a 8-foot tall fence behind me. There's my house, which is 2 stories. So there's all kinds of stuff that is in the way. So this isn't a true anechoic measurement as much as I'd like it to be. It's just not. And if you measure a horn too near field, then your response doesn't. It's not quite right. There's reasons for that. But yeah, I basically couldn't get the microphone far enough away and not pick up ambient stuff. So I have a feeling that they're actually even a little bit closer. So that's, to me, that's even this amount of agreement. It's not bad. Like, this is pretty good agreement. My guess is it's a little closer. So one of the things that you have to realize when you have this sort of imperfect horn, right? This mouth is too small, right? Is that when you put two large front-loaded bass horns together side by side, they acoustically see each other and they will help each other out. I think we just went from Phytal background to BNC. Sorry, Jason. You're welcome, Bennett. So they see each other and they get benefit. Now let me show you because horn response actually measures or models this pretty well. Okay, and I've confirmed this multiple times. So first off, let me capture these results. So what I'm going to do is I'm going to change the input voltage from 2.83 volts to 2 volts. Okay, calculate, tools, multiple speakers. And now I'm going to put two whole speakers in parallel with each other. Now, by going from 2.83 volts to 2 volts and doubling the number of speakers, I'm keeping the input wattage the same. Okay? And now I'm going to compare captured. Okay. See how at low frequency I actually get a boost there? That boost is real. They help each other out, and you have even higher sensitivity than you otherwise would. Okay, and this has been shown. I have shown this with Hennessy battle axes. I have been lucky enough to measure a fairly large block of them in a field. To do it at any reasonable input power, to start looking for compression, things like that, I had to put the microphone 70 feet away. But this benefit is real, okay? I can show you even more benefit. We're going to start losing the... actually, hold on, let me go do this. 2.83 volts. Calculate. So now, let's say you were running a fairly large festival and you put 6 of them in parallel. Lo and behold, a lot of that ripple that was in that response, tools, compare captured, all like this up and down ripple has gone away, right? Because now I've made the mouth large enough. They all sort of couple to each other. Tapped horns don't get this benefit, or if they do, they don't get it nearly as much. I don't think they get it much at all, actually. And even horn response shows that in the modeling, if I remember correctly. It's been a while since I've checked that. All right, so what are some other cool things that horn response does, right? It'll show you, of course, the diaphragm displacement, group delay. All those are neat, right? You hopefully, if you've used horn response at all, you'll recognize those things. But let's go back to acoustical power and double click on efficiency. It actually will calculate for you the electrical to acoustical efficiency. And this is where you can see this horn does pretty well, right? It has, up in the higher registers, it actually has quite high efficiency. It's pretty unheard of, but it is actually happening. But for, you're not going to get easily at 80 hertz, or what frequency is this? 70 hertz, 60-something% efficiency, okay? The other thing it will do for you is, if you go to output, port, whoops, let me do this, output horn, okay? This is the output of the horn by itself, and I'll talk about that port in a second, Okay. Tools, sound pressure, throat chamber exit. It will actually calculate the amount of pressure in pascals, which you can convert to PSI, on the driver diaphragm. Okay. And this is useful because as you start running into these higher compression ratios for these horns, and this horn is a fairly high compression ratio, you need to start watching this. If you see this compression ratio at significantly, or this pressure at significantly higher than what you would see in a vented box, then you need to start worrying about your cone integrity. It is entirely possible to rip cones in a front-loaded horn. I have never done it. I am waiting. I think it's an inevitability with how hard I tend to drive some of these things. But we'll wait and see, right? So the thing that it will do, wait, did I just, sound pressure, wait a minute. I'm showing you the wrong pressure. That's the acoustical pressure. That can get converted to acoustical power. I know which one. Sorry, diaphragm displacement. That's the acoustical power pressure. Diaphragm displacement. It will actually calculate diaphragm pressure. Sorry, bad Scott, bad. And what you want to look at is the total, okay? Again, it'll show you this in peak pressure. So what I'm going to do is go to save changes current record. I'm not sure what I've changed all at this point, so I'm going to say no. So what I'm going to do is I'm going to look at this is the same driver, but in the Speaker Freakers Dual 18 box. Again, this is at DIY or the Facebook page here. If you go to diaphragm displacement, tools, diaphragm pressure, total, I'm going to capture these results. Tools, diaphragm pressure, total. It shows you the peak pressure on the cone, and for a bass reflex speaker, that will happen at the typically at the tuning frequency, because that's where the driver is held by the air pressure, the reactance in the box, right? So now let's go back to there we go. Diaphragm displacement, diaphragm pressure, total, compare. So in this case, you can see where the diaphragm pressure on the horn is higher. Now, the fact that in this frequency range up here, it's higher than the vented box, I'm actually not that concerned about, because the cone, the peak pressure here, those cones don't rip themselves apart, right? If you're operating them that hard on a vented box, it would be if this peak was 4 times as high or twice as high as this. This is 10, 20% higher. And so you do have to be careful. Like if it's a sort of a floppy coned woofer, odds are it's probably not going to be a great match to a bass horn. But these SB and some of these other woofers from Vital Pro and B&C and folks like that tend to have very, very stiff cones. In general, I have found, and I don't want to say this as sort of some rule of thumb that's guaranteed and the way it should go. In general, the drivers that have the ribbed cone tend to have a little stiffer profile and tend to be better for this. I have seen some sort of but I've seen exceptions to the rule where the cone is sort of smooth and flat. Let me see if I get a picture of what I'm talking about instead of waving my hands. So this is the SB driver that's in here. This ribbing in this cone tends to be a bit better suited. You can grab that cone and sort of try and flex it, and you see where you're moving a lot. You're basically moving the whole cone instead of bending that local area. Don't do that too hard. Don't put a thumb through a cone. I don't want to ruin your day that way by suggesting you do that. But yeah, so this level of difference, I don't worry too much about. The big peak in pressure down here, now we're starting to talk where this is almost twice the pressure. But odds are this device will be run with a high pass filter to prevent subsonic frequencies from taking up too much of that excursion. So, let's see. What else? Ports. I mentioned that I was going over with the ports. Okay. So the ports in this woofer, and I have tried, or in this horn design that I've got behind me, the ports are not designed for low frequency output. I don't care. Their output is so negligible compared to the horn itself that I'm not using them for output. I'm using them because front-loaded horns, especially for big ones for PA use, tend to have a problem in that you take this driver and you put it in a tiny box that's sealed. The front of the cone can't see the outside air. The back is completely enclosed. And so now this driver has no way to cool itself. Within the PA industry, it is well known that this happens, or at least with the folks that are experienced with big PA horns. And you will see some, for what are otherwise very high output speakers, some long-term limiting settings that you're looking at them going, that seems really low. But if you can't get the heat out of the box, it's realistic, right? If you think about how hot a 150 watt light bulb gets, if you put that 150 watts into a 3 cubic foot box, and that air temperature in there is going to be raging in no short order, and you'll actually burn up those woofers pretty quickly, right? Whereas if you put them in a vented enclosure where there's heavy air exchange through the vents, all of a sudden that air there's some fresh air replacement. JBL had a great paper on this in the AES. So what I did is notice that I took output port, tools, compare captured. Whoops. Come on. Release captured. Capture results. All right. Tools, compare captured. So right now you're looking at the output of the port versus the output of the horn. Notice how little the port actually does for this thing. It is solely there for air exchange. Okay. So now we're going to go to another feature in horn response that let's see. Another feature in horn response. Let's see. Any questions? I'm flying here, so I don't want to. We are going to add a filter. Filter Wizard. High pass. Fourth order. Actually a little high for this. So now I have put on a high pass filter. And now you can see where I've kept the displacement at low frequencies down. And you can see where I've kept that diaphragm pressure way down. Okay, so now I have aided this quite a bit. But if I go to acoustical power, tools, output, port, tools, particle velocity, port, I actually have not a tiny port velocity here, right? So if I go to a drive level that is more apropos, oh, not 300 volts. Woo! That's a cone fryer right there. Actually, actually, let me go back to tools, Windows, acoustical power tools, output, combined. Okay. Yeah, this is a level that you hit all the time in Pro Sound, right? For periods of time, you know, even higher, frankly. Wait, tools. I think my filter turned off. Maybe it didn't. Nope, filter's still on. Okay. Tools, output, port. So now I've got higher output in the port. Particle velocity. Lo and behold, that is the type of port velocity that you would see. And in fact, since it's over 17 meters per second there, the air is going to be going nonlinear, and you will start to see significant air exchange through those ports. I have worked for the last 3 weekends to try and figure out a way to demonstrate this without destroying the structure of my house. Yesterday, I made a valiant effort with some power dissipation outside of the drivers. I had big resistors on big heat sinks and things like that. But at some point, I just need to find myself a field or an airport hangar and just toaster test these horns, because every time I try this, either the volume is so high that I have to turn it down for fear of a noise ordinance violation, or the test is so far from reality that it's not working well. I know this works. The JBL folks showed this in the paper for bass reflex horns, or for bass reflex boxes, but I just can't seem to show it on these. So let's see what else. So those are some of the fancier features. There's a lot of stuff here in terms of being able to show particle velocity, pressures, diaphragm displacement, and things like that. I am a big fan of looking at those when you're doing horn design, right? If you're looking at just frequency response, and Bennett Prescott from BNC has gone into this a lot. If you're looking at just frequency response, the horn, what you see may not sort of meet this classical definition of what you'd like to see for good frequency response, like, you know, the QB3 alignment where you've got a nice smooth thing. In horns, you're just not going to get that until you get huge groups of them. What else? What else? All right. I've gone through a lot. What other questions do we have? Because we're coming up on 12:47. And while we do that, we're gonna see how well this does. Yeah, there we go. I have my wife is gonna kill me. I don't know if she's ready for this. So I thought I'd give a little demonstration of the horns. Yeah, let's see how this goes. Oh, did you guys hear that? Did you guys hear that? Did you see that? Yeah. Yeah, I'm getting blasted with about 130 decibels of 40 hertz, 31 hertz here. What I do for science. I'm having way too much fun now. Any questions? Daniel. Should I hit it harder? Oh, sorry. I should have warned. Yeah. The U mic is not going to get overloaded by that. Not where the distance it's at right now. Sorry, I should have given you more warning. So yeah, these things really pound. I have taken drywall off my ceiling I have done almost damage to the garage door. I thought for a while it was going to come off the rollers. Not that funny, yet funny. Yeah, I should have given you guys some more warning on that. The tone bursts can be quite a rude awakening. And let me talk about the driver that is in here a little bit. Our peer pressure worked. Yes. So Brian did a spreadsheet for this horn fold. It's, if I remember correctly, it's half the horn, right? So you'll have to sort of double all of the areas and things like that, because it's only giving you one half. So if you simulate it and you see an even raggedier response than you expect, that's because the mouth is way too small. It's only half the size that it should be. Or just make a really big version of one of these horns, and that's fine too. So the driver I'm using is from SB Audience. They are known for their SB Acoustics drivers, probably a lot better, although in the Far East they're fairly well known for their PA drivers. I have in this box the 18SW1000D. It is a pretty heavy duty driver. It's got one little issue on the spec sheet. I swear they mean X max or X damage of 25 millimeters one way, even though this note says two way. But healthy X max, healthy power handling, voice coil diameter, shorting ring. I don't have a good picture of it here, but yeah, Brian did a great job on that. So we should all, thank Brian for doing the horns. Those spreadsheets, they're really handy. It would have saved me a lot of time. I probably should have just sent him an email and said, hey, this is the fold I'm thinking of. Can you do this? Would have saved me a lot of time. This device actually has effectively a vented pole piece, but they have like little heatsink type pieces inside the pole piece to pull even more heat out of it. Again, I don't know exactly how effective they are because because I haven't been able to bake these drivers. I've actually purchased a very high power amp for those kinds of things and haven't gotten the chance to play with it yet. So one of these days we will do that. One other thing that I wanted to get to, and it comes to this one, is a lot of people ask about the Lossy LE. I got asked the last time I did a horn response video. I've looked into it. I haven't fully made up my mind yet. I reserve the right to change my mind, but right now I'm not a fan. And this is why. I'm going to go to horn response, and I put my next project is going to be using the Eminence NSW 4018s. I still don't know exactly what I'm doing with those. I'm trying to do something more than just a normal vented box. It might be that, but it might have some fancy ports. Might not. I'm not sure. Yeah, so Brian brings up the semi-inductance, right? Lossy inductance, I'm not a big fan of. Semi-inductance, I think I am. I need to dig into that one even more than I have the lossy inductance. The lossy inductance was based on a spreadsheet curve fit that, as far as I can tell from the paper that I've seen on it, doesn't have a lot of pro sound drivers, and it assumes that how do I put this? Basically, they curve fit on inductance versus BL, and they curve fit to frequency response shape, right? There's a problem with that. So if I double click LE, whoops, I got to edit it first. If I double click LE and I hover over BL for this eminence driver. The spec sheet for the driver, it has a BL of 29.24, okay? If you hover over it, it says that the adjusted BL is 24.2, okay? If you look at the Klippel curve, which directly measures BL, nowhere on this curve does it drop below 25, okay? So what's happening is, and it's a pretty big, it makes a pretty big difference in this one. So capture current results, calculate, tools, compare captured. Right? So the difference in terms of response is not trivial, but even the folks, the paper I read, and I forget, I think it was just a guy on DIYaudio.com. He's like, but the impedance is wrong and things like that. Well, if the impedance is wrong, does that mean your excursion's wrong? Does that mean all these other parameters that I just showed that right? There's some issues there, right? So I think it's a proxy for something else that's going on in the modeling, or even the measurement technique. I'm not 100% sure where it is, but because it changes one parameter and one parameter only to a value that doesn't actually represent what's physically measured, I'm not a real big fan of it. This is something that has been bothering me about the Lossy LE for a while. The semi-inductance model, is better, right? And if folks like Andrew Jones and folks like that, Scanspeak and folks like that are swearing by it, okay, yeah, I'll pay attention and believe it then. But the Lossy LE, I'm not a big fan of, and I don't think it's the right way to go. Any other questions? That wasn't even a question that I just dove into. But yeah, next project's going to have these guys, the Eminence, and as I said, these things are beasts as well. I'm looking forward to this. I'm trying. The only reason I haven't done something faster is I want to do them justice. They're when you hold them in your hands, you're like, oh, that's pretty serious. So I also have a set of 18 XL 2000s that I've done an entire box around, a bunch of measurements around, but have never turned it over as a project. So I think that might be a fun head-to-head between the two of those. Any other questions? Because we are coming up on 1 o'clock. See, I'll wait for folks to type it, because there's more of a delay here than I realized when I did the last one. It was driving me nuts. It didn't drive me nuts. Why is there a limited option for small sub, high efficiency, and cheap price? Because it's all really hard to do. Sort of the phrase cheap, fast. If you want something designed and it needs to be cheap, fast, and good, you can only pick two, right? Well, small, high efficiency, and cheap. I don't think you can pick any of them. It's really tough. I mean, these subs behind me weigh 310 pounds each. I don't know if you can see it, but in my garage ceiling, I installed. Oh, that's a good tip. Brian. I'll try and steal that. Use a very low level of stuffing to emulate box losses. That's actually a really good tip. There is an electric hoist on my ceiling. These boxes have internal fly points on them so that I can hook up to them and hoist them, because I can't get these into a vehicle myself, obviously. They are designed for the North American sort of full-size pickup truck. They are not necessarily designed for box truck pack. Their external dimensions are 2 foot by 4 foot by 4 foot, which means on a full-size pickup truck in the United States, you can put 4 of them in there. I actually have a picture on DIYRM where I actually have a 6-foot bed. I have a short box truck where I have 2 of them and I've sort of stacked the entire PA system and just into the back of the truck. So they're stupidly handy for that and for installs. They would never be all that great for the touring market because they're not a great match for the box truck, which is typical for the touring market. But if you want a lot of bass, you need to have something this large, or you need to have size and amount of bass is directly proportional. You just can't get a tremendous amount of bass out of a tiny box. Yeah, that's the Hoffman iron law for sure. And I mean, one of the things that these horn subs were as much about the exercise for the venting and for confirmation. And I have measurements. I'm putting together a design paper for these things as well. The confirmation of that horn response modeling where the two subs couple. You actually see that. In fact, let me go show you that real fast. Window, schematic diagram, window, input, previous, yes. Not the dual 18. Actually, hold on. Okay, calculate. If I look at capture current results, if I look at the electrical impedance, notice I've got a peak, let's say, right at 37 hertz, right? And it is, what, 11.5 ohms. If I do tools, acoustical power, control K, 2 in parallel. Notice that the impedance has dropped because there's 2 in parallel. Actually, wait a minute. Tools, acoustical power, tools, multiple speakers. 2 in series, 2 in parallel. Now we'll bring it back up to dang it. Window. Here's where I'm trying to go too fast. Electrical impedance. Tools, compare capture. So notice how I did 4 speakers, all right? The light gray line is actually 4 speakers. It's 2 in series, 2 in parallel, so it's got even more mouth area that are coupling together. Notice how the impedance peaks have dropped and shifted down in frequency. And if you were able to zoom in a lot, you'd actually see a bunch of areas where the overall impedance came up, okay? That actually happens. Like, that's the easiest way to sort of verify that that's happening. I can do that pretty easily even in my setup where I just point the speakers out of the garage door, measure the impedance of one with the other one shorted, turn the other one on, and all of a sudden they're not electrically in parallel. They're just separate channels, right? They're totally separate channels of the amplifier. And the speaker that I'm measuring impedance shifts, right? So you can actually see that. You don't see that impact on direct radiators nearly as much. It's microscopic, okay? Right now I have a cheap 10-inch sub with fudge silly smalls. Can't seem to get a good response, whatever the model of the box. Yeah, I mean, there's some drivers that have just really bad parameters. If it was a really inexpensive driver, I've seen, inexpensive 10, 12-inch woofers with a QTS of 1.5, and there's really not a lot you're going to do at that point except put them in a small box and EQ them and hope that you can get enough power into them that they don't burn up and enough output power. So that's about your only choice. Unfortunately. All right. Anything else? Was there anything else that anyone wanted to see? Shove it up against the wall. Yeah, it's always easier to look at impedance. Brian is right. It's if you can get that impedance simulation to be on then you know physically what's happening. So, if you're looking if you're in the United States, and you're looking for SB audience, go to Matasound. That's who has them now. This driver is available in the United States. They are available other places. I have gotten some questions previous on where you can find these. Any other questions? All right, everybody. Well, thank you so much for joining me for this hour and 10 minutes. And we will see you next time. If anybody is looking for, or I am actually looking for hints on what I should present next time, I've got a couple of ideas. But if for the next live stream I do, shoot me a PM. And where are they built? They're built in Indonesia, in their factory in Indonesia. So they do a lot of OEM work. I have actually talked with some representatives from their company at NAM, NA, National Association of Music Manufacturers Conference. It's not my place to sort of talk about who I know they've OEM'd for, but they've OEM'd for some pretty big companies, and their drivers are in some pretty big companies' boxes as well. Anything else? Anything else? Do watch if you are looking at these SB boxes, SB drivers, they are not necessarily drop-in replacements for other drivers. The bolt hole pattern and the cutout is a little different. Just warning you. This frame, this is really like an 18.5-inch driver. So do be careful of that. They will not plop into a cutout for like a 18 TBX 100 or something like that from BNC. Yeah, that was an interesting choice. It's sort of reminiscent of the PHL drivers, Brian. I don't know if you remember those. They're much harder to get in the United States now than they used to be when Xalotron closed down and was the reference. But they're same. Yep, Precision Devices frames. I actually like that frame a lot, the octagonal frame a lot for rigidity on the baffle. It makes it very easy to get the T-nuts in and still have plenty of wood to bite into and things like that. But the drawback for these anyway, as I said, is that bolt hole pattern's a little bit larger. Let's see, I don't think I have the other one. Let's see, what is the 456? Where's the bolt? Yeah, so like a Phytal Pro is 440 millimeters, and SB is 456. So just watch that, right? It's enough that it's not gonna drop in. But they are very, very nice drivers. I have been when I pulled them out of the box the first time, you should have seen the look on my face. Like, ooh, look at that! They're fun. And as you can tell from the poor in-ear monitors and subwoofers that have been listening to me, that I should have warned, the output is substantial. I probably won't build a double 18 reflex box because I already have 3 of them sitting over there for these, but they would also work very well. In fact, input next. If we do this, capture current results, Windows input, calculate, tools, output, compare capture, release. I am previous. I was still at 50 volts, which is not fair. Capture current results window. Next. Yes. Calculate. Tools. Compare caption. So that's the difference between these two driver, or the same driver in the Speaker Freaker's 18-inch bass reflex versus the horn. So you can see what the horn buys you in terms of additional output for your money. You just have to build a much more complex box, much more. So, all right, everybody, I'm gonna go eat lunch, and everyone have a good day. Talk to you later. Bye.